Okay. So welcome, guys. So this video, let's talk about Bolzano Weierstrass Theorem. Okay, I just want to make sure that Bolzano Weierstrass is an interesting theorem, so I want to make a small video for it, and be sure to subscribe to my channel. Okay. So let's quickly see. So what's Bolzano Weierstrass, right? So given xn, basically is the so this is not bad notation. So given a sequence in Rn, and this xn is bounded, then there is a convergent subsequence. Basically, xn1, xn2 up to infinity will converge. So bounded sequence must exist a convergent subsequence. Okay, this is very strange result that you guys may think, which is not true. But so let's focus on proof. So the proof is that let's suppose we go to R1, right? Let's suppose you go one dimension. So you given xn, and then there's a thing called a peak lemma. That's prove it. So peak lemma, I say that if somebody give you xn, right? So this xn cannot be may not be bounded, okay? But there's always a monotone sequence, a subsequence. Basically, if somebody give you x1, xn1, xn2 up to infinity, then you can always pick some of them, such that they're all monotone, they're all increasing or decreasing. Okay, so this proof is very interesting that you take A, which is a set, basically all the integer m, such that for all n greater than m, xn will less or equal to xm, right? So you need to you want to choose some m such that all the sequence label greater than m will less or equal to xm. Okay, so this is it. So there's always two possibilities. The first possibility is the cardinality of A is infinity. This means that you can pick up m1 in A, right? You pick m1 in A, then by definition, all the number greater than m1 will less or equal to xm1, right? So you can pick up m2 and pick up m3. That by definition, things are laid out all in A, right? So xm1 greater or equal to xm2, greater or equal to xm3. So keep going. So this is the monotone decreasing sequence. Otherwise, that A is finite, right? If A is finite, then you pick the m1, which is max greater than all the A. M1, right? By definition, since M1 is not in A, so you can always find M2 such that xm2 greater than xm1. Then M2 is not in A, so you can always find M3 such that xm3 greater than xm2, right? So keep going, you can find a monotone increasing sequence. Okay, so we proved the lemma that however you want, right? For however somebody give you a sequence, you can always very kind and pick the pick out the monotone sequence. Okay, so there's an additional additional condition that now xn is bounded, right? But you can always find a convergent sequence. You can always find an increasing or decreasing subsequence. But now by the completeness of real number, if you have something which is increasing and bounding above, or you have decreasing or bounding below, then there are always a converge subsequence. So this subsequence will converge by the monotone convergence theorem. Okay. So now we prove the Bolzano Weierstrass in the Rn equals to 1, right? Now we go back to Rn. So go back to Rn is also trivial, right? Take an example. So you can take each component. So for example, somebody give you original sequence, then you pick up subsequence which the x1 will converge. So you first forget about all the rest minus one component, and then you focus on subsequence that's x1 will converge. Then you keep pick up, right? You can pick up you can select the particular points in this x1 in this subsequence, and then you do the subsequence of subsequence such that x2 will converge. Then you do subsequence of subsequence of subsequence, and finally you can pick up the subsequence of this, which that all the coordinate converge. And by definition, series converge means that each component converge. Okay, so yeah, the proof is done. And the next video, we may talk about the key to calculus and the continuous function. What's the Bolzano Weierstrass? And also we can use the Bolzano Weierstrass to prove a famous theorem called the Henry-Borel theorem. So basically, it's all the closed and bounded set in Rn is basically the compact set. This is also okay, but let's talk about a small application of the monotone convergence sequence, which we mentioned. So this sequence, the first time when I see the undergrad, then I feel this theorem is very stupid. So it says that if you have I1, basically this closed interval, and there's another called I2, I3, and you keep going, and each of the interval are contained in the previous. Okay, then if limit n goes to infinity, the in will be 0, means that if the sequence length will be arbitrarily small, if you intersection all the interval, then you get some points x naught, which x naught is in AB. So this looks stupid either, right? If you imagine that you keep growing, you keep shrinking, and finally you will hit some points, right? But this is basically showing all the completeness property of the real numbers, right? So suppose, you if you see the rational number, then finally this intersection may hit some points, but that point will not be rational, right? So basically the property of the real number actually shown exactly in this example. So proof says that if AK, let's say AK, right? So by definition, AK decreasing and bounded below, right? Why? Okay, sorry, I think I missed something. The AK is the left interval, so I should write. Let me just change a little bit. Okay, so sometimes I write note, but the note has some property. So actually so you see this is A and B, right? So now you get A2, B2, keep going, right? So A2, right? B. So you see AK, right? AK will increase BK. So AK will bound it above, right? Because AK is bounded by B. So above, and then this is below. So by definition, by the Monotone converge theorem, we know that AK must converge to some A bar, B converge to some B bar, right? But their length must be 0, right? So they must converge to the same point, and so this contains some point x0. Basically, are all the limits of these two. Okay, so this is the proof. Okay, and actually one can use this Bolzano Weierstrass theorem to prove the intermediate theorem. So we will use Bolzano Weierstrass to prove many obviously calculus and continuous function results, which are so amazing that actually I'm not completely understand what I was under. Okay, I will see you guys in the next video. Please subscribe to my channel. Thanks.